whether the charges move from hair to comb or from comb to hair. Who loses electron and who gains electron, and what decides that? So the objects like human hairs, asbestos, rabbit fur, nylon, wool, etc. tend to lose electron and become positive charge. Whereas objects like acrylic, rayon and polyester tend to gain electron and becomes negative charge. The objects like paper, cotton, steel, wood, they are kind of neutral objects. When we rub plastic comb on our hairs, the hairs tend to lose electron and plastic comb tends to gain the electron and becomes negative charge. This process of charging by rubbing happens for few specific pairs because in this process of rubbing very limited number of transfer of electrons takes place, because transfer of electrons takes place of the electrons which are less tightly bound to the nucleus. Therefore, we need an electronic configuration which supports this. Therefore, only those elements which have that suitable electronic configuration can be charged by this method. This charging by rubbing is not supported by conductors because conductors are good conductors of electricity and they conduct all the electrons within the surface, and there are no free electrons on the surface. Next method is charging by contact, that is conduction. So in this method we take a charged object. Here the charged object is negatively charged and we have another uncharged object. So when we bring this uncharged object close to this charged object, what happens? Here you can see this is the charged object and this is the uncharged object. Uncharged object too have charges. So what happens? The positively charged charges get drifted towards this end and the negatively charged get drifted towards this end. Now what happens? This positive charge of the uncharged object, they attract these negative charge of the charged object, and due to this attraction what happens? The excess negative charge move towards the uncharged body. So this object also gets negatively charged. Similarly, we can also charge any object as positive charge also. In this case, we'll have to take this charged object as positive and uncharged, and we'll have to take one uncharged object. Another method is charging by induction. So in charging by induction, actually there is no contact between the charged object and the uncharged object. So what actually happens? In charging by induction, we take a charged object and an uncharged object and we bring close the charged object and the uncharged object, but they don't have any contact in between. So what happens? So in this method what actually happens? These drifted positively charged atoms, these are the drifted positively charged atom and this is the negatively charged atom. So when we earth this object, what will happen? These negatively charged object will go to earth and this object will becomes positively charged. Similarly, we can charge a body as negative charge. So induction charges a body with the opposite kind of charge. Let us discuss about some properties of charges. So first property of charge is additivity of charge. So the total charge on a body is the algebraic sum of all the charges located anywhere on the body. Next property is conservation of charge. So this conservation of charge tells us that the total charge of an isolated system of objects is always conserved. The transfer of charge may happen, but the net charge of the system remains constant. For example, suppose this is an isolated system A, B and C. These are three objects in this system. So A object is having 6 coulomb of charge, B object is having 4 coulomb of charge, and C object is having 8 coulomb of charge. Now if we shake this system for some time and bring it to rest, and after some time we find that object A has got 3 coulomb of charge, object B has 9 coulomb of charge. So what will be the charge on object C? So by the conservation of charge, what does the conservation of charge tells us? It tells us that the total charge of an isolated system of object is always conserved. So total charge of this system before we have shaked the system is, let us see, 6 coulomb plus 4 coulomb plus 8 coulomb. So how much it is? 6 plus 4, 10. 10 plus 8 is 18 coulomb. Now here, after shaking the system, what is the charge on A? Is 3 coulomb. Charge on B is 9 coulomb. And charge on C, we don't know. So what is the total? Total is 12 coulomb plus X. So what will be the value of X? We can easily find out. So X is equals to 6 coulomb. So with the help of conservation of charge, we can find out the value of charge on the object C. Next property is quantization of charge. It is very important property. So let us see. Any charge Q in nature is an integral multiple of the electronic charge. So mathematically we can write it as Q is equals to NE. So what is Q? Q is charge on body or object. N is any integer. E is the electronic charge and its value is 1.6 into 10 raised to power minus 19 coulomb. So quantization, what does this quantization word means? Quanta means a fixed number. So what it says that the charges also exist in nature as an integral multiple of electronic charge. Just like if I wish to purchase a duster or a pen, so I can purchase 1 pen or 2 pen or 3 pen or n pens, but I cannot purchase 1.5 pen. So it is not possible. Why? Because pen comes in fixed number. In the same way, charges also comes in fixed numbers. You cannot have 1.5 coulomb of charge. You cannot have 8 by 7 coulomb of charge. You cannot have. So charges always exist as the integral multiple of the electronic charge. Next we'll study about the Coulomb's law. This is also very important law from your examination point of view. So Coulomb's law states that the force between 2 point charges varies inversely as the square of distance between the charges. So if Q1 and Q2 are 2 charges, they are separated by distance r. So what it says, it varies inversely as the square of distance between the charges. So this force between Q1 and Q2 is denoted by F. It varies inversely as the square of the distance between the charges. Okay, and it is directly proportional to the product of the magnitude of the two charges, and this force also acts along the line joining the two charges. So if we use these two things, what we can find out, we can merge and we can find out the value of F. So F is equal to, when the proportionality sign is removed, we get a constant. Okay, now F is equals to K Q1 Q2 upon R square. K is equal to 1 upon 4 pi epsilon 0, where epsilon 0 is the electrical permittivity. Value of epsilon 0 is 8.85 into 10 raised to power minus 12 coulomb square per Newton per meter square, and the value of K is 9 into 10 raised to power 9 Newton meter square per coulomb square. Next we'll study about the nature of electrostatic or Coulomb's force. So this force obeys the principle of superposition. That is, presence of third charge does not affect the forces exerted by 2-point charges, but the net charge is the vector sum of all the forces on the charges due to all other charges. Second property is, it is a central force. What does it mean? It means it acts along the line joining the object and the origin. Next is, it is a conservative force. Then you have studied about the conservative force in class 11th also. Next property is, 2-point charges exert force of equal magnitude on each other. So the force is mutual force also. Next property is, it does not hold for the charges that cannot be treated as point charges. This force has a range of 10 raised to power minus 15 meter to a few kilometers. Next property is, we can define 1 coulomb of charge on the basis of electrostatic force. That is, 1 coulomb is that charge which, when placed in vacuum at a distance of 1 meter from an equal and similar charge, would repel it with a force of 9 into 10 raised to power 9 Newton. Next thing we'll study about the charges is principle of superposition of charge. So this principle says that total force on a given charge due to a number of other charges is the vector sum of individual forces exerted on that charge by the other charges. Each individual force is unaffected by the presence of other charges. So suppose F1 is the force on Q1. F1 is the force on Q1 due to all the charges present here. Suppose there are other charges Q2, Q3, Q4 and Qn charges. So this F1 will be the vector sum of all the forces on the charge exerted by the individual charge. Now let us see here. So F1 will be equal to force on Q1 due to charge Q2 plus force on Q1 due to charge Q3 plus force on Q1 due to charge Q4 and so on till force on Q1 due to the nth charge present there. Okay, now let us see, suppose R1, R2, R3, R4 and Rn are the position vectors of these charges. So how we will write force on Q1 due to Q2 by using Coulomb's law. So it can be written as F12 is equals to K Q1 Q2 upon R21 square. This is the distance between these two charges and this is the position vector. So how we can write the general equation for any charge Qi? So we can write it as Fi is equals to K summation I ranging from 1 to n Qi Qn upon Rni square and position vector R cap Ni. So this is how the principle of superposition of charges helps us to find out the force on any object or any charge where another charges are also present. Next is continuous charge distribution. So when there is an extremely close space, so the extremely close space charges from continuous charge distribution. So for this we must know about charge density. What is charge density? Charge per unit dimension. So there are three types of charge density. One is linear charge density denoted by lambda. This lambda is equals to dq upon dl. dq is charge, small charge, and dl is the small length. This linear charge density is useful for finding continuous charge distribution in a rod. So linear charge density is charge per unit length. Next is superficial charge density. It is denoted by sigma. It is equals to dq upon dA. It is charge per unit area. Next is volumetric charge density. It is denoted by rho, that is equals to dq upon dv, that is charge per unit volume. And it is used to study the volumetric charge density just like in cube, etc. Next is electric field. So electric field is the region around a charged body in which another charged body experiences an electrostatic force. So suppose there is one plus q charge, this is a source charge, and there is another charge q0, this is a test charge. So plus q charge will produce electric field around it, but this q0 charge, this is the test charge. So test charge is considered as it is having it is very small, it is negligible and does not have any electric field. But the source charge, it produces electric field. So what is an electric field? Electric field means the region around a charged body or the vicinity around the charged body where its force can be experienced. Next is electric field lines. So electric field lines are the imaginary lines which represents the electric field. So these imaginary lines, they act radially outwards for a positive charge and they act radially inward for a negative charge. So suppose this is a positive charge, so the electric field lines will act radially outwards for a positive charge, and for a negative charge they will act radially inwards. Here you can see the electric field lines for two positive charges. So here this is first positive charge and this is second positive charge. So this is electric field lines for two positive charges. You all know that positive charges, they repel each other. So electric field lines, they tend to repel each other. They do not touch each other. The electric field lines of the discharge and electric field lines of discharge, they do not touch each other. They repel. And you can see here, this is electric field lines for a positive charge and a negative charge. So these lines, the positively charged particle or the charge, the electric field lines, they act radially outwards, whereas for a negative it is radially inwards. So these lines tend to move from positive charge and enter the negative charge. So this is how we can draw the electric field lines for a positive charge and a negative line. These diagrams are important for your examination also. Next is the properties of electric field lines. So the first property of electric field lines is no two electric field lines ever intersect. It means that if there is an electric charge and it is emitting electric field lines, suppose this is a positive charge, so no electric field lines will intersect. Why they will not intersect? Because if they will intersect, so the electric field lines actually gives the direction of electric field. So whenever they will intersect, so what will happen at the point of intersection? If electric field lines, they will intersect, so what will happen at the point of intersection? When we draw a tangent, you would have studied for the magnetic field lines in class 10th also. So the tangent to these field lines will show the direction of electric field. So at one point, two direction of electric field is not possible. Next property is field lines are always perpendicular to the conductor. Next is number of field lines is directly proportional to the amount of charge. So suppose you have three field lines which are coming from one charge, and there is another charge Q2 which is emitting out 5 field lines. So what does it mean? That Q1 has more charge, Q2 has more charge as compared to the Q1. So number of field lines is directly proportional to the amount of charge. Next is field lines contract longitudinally during attraction between the unlike charges. So here you can see positive and negative charges, they attract each other, and you can also see that the field lines are contracting. They are not spreading out just like in this example. Here you can see they are spreading out. They are spreading out. Here they are contracting or converging. So field lines contract longitudinally during the attraction between the unlike charges, whereas the field lines exert lateral pressure during the repulsion between the like charges. So for like charges, what happens? They put on the lateral pressure. They put on the lateral pressure, due to which they go away from each other. Next is the uniform and non-uniform electric. So uniform electric fields. Uniform electric field lines are equispaced. Here you can see these lines are equispaced, whereas the non-uniform electric field lines are not equispaced. Here you can see the electric field lines, they are close to each other. Here you can see they have different spaces between them. So uniform electric field is equispaced and non-uniform electric field is not equispaced.